All right, let's get started. So the main focus of today is going to be on Tuesday's lecture, which was on state space models. So before I forget, I have a short feedback form on just overall discussion feedback. And this is specifically for my discussion. So even if you're watching this online, definitely take the time to fill this out. And this is just a mid-semester temperature check just for you to kind of voice how these discussions have been going, whether you think the pace is too slow or too fast, or whether you think whether you have any problems with the format, I guess. And especially for those online, this is a chance for you to kind of get the time to voice your opinions as well, because you can't directly ask questions. All right, with all of that in mind, let's just do a short recap of what's been going on in the class. So kind of coming to an end of the circuits module, but this is really the main takeaways from the circuits module, where we looked at how to model circuits in both time and frequency. And in time, we mainly used differential equations, and differential equations were the language of time. And we also learned how to model circuits in frequency using phasors. And the cool thing about all of these phasors were that they are all time invariant, meaning they don't depend on time. So you can think of it in a different kind of setting or a world where time doesn't exist. And to solve the RC cascaded example, you might remember this example, or the RLC circuit, we kind of used this multivariate or vector differential equation of this form. Dx dt was equal to ax plus b. And this is kind of going to be the really main important takeaway from the circuits module, where today we're going to be looking at a bunch of new models which kind of expand on this idea of the vector differential equation. So we're going to be looking at a bunch of other systems that have similar properties that aren't necessarily circuits. So we're going to introduce what a state space model is, and just kind of a recap from lecture, but a state space model consists of these variables, x1 through xn, kind of the same way we saw in our vector differential equations, called states. And we're going to have these new variables, u of 1 through u of m, called inputs. And inputs are kind of new, but the main, I guess, kind of way to think about inputs are a way for the person designing the state space model to control the state space model. So a really quick example I can give is if you have a car and you're let's say you're driving your car out on the road, you can think of your gas pedal as an input, where if you push your gas pedal, you accelerate with your gas pedal, it's going to move your car forward. And if you kind of, I guess, release the gas pedal or press the brakes, you'll notice that the car starts slowing down and maybe goes backwards at the end because of some under damping. But you can think of the gas pedal as an input, and we're going to learn how to model inputs today. And with any state space model, the model really refers to the equation. So we're going to be thinking about state space models in two forms. We're going to be thinking about them either in continuous time or in discrete time. And in continuous time, we're going to be using our very familiar differential equations. So we're going to have differential equations. Our time variable t is going to be a real number. And in discrete time, this is kind of new, but we're going to be using something called a difference equation. And a difference equation is just a recursive equation that kind of tells you what x of t plus 1 is based on x of t, its previous time step, and its potentially input. So the t variable here is going to be a natural number. So it's going to be equal to like 0, 1, 2, so on and so forth. It's going to be a natural number. And while these two systems are, they kind of look similar on paper, you have this like f of x and u. We're going to learn a lot in this module that the two kind of behave very differently because like one of them is continuous and one of them is discrete. They're kind of fundamentally different systems. And I think the last thing I wanted to say is like we focused a lot in like the circuits module on solving these differential equations, but going here onward, we're much less going to emphasize solving. We're much more going to emphasize like understanding properties about these differential equations and these state space models, which help us kind of learn and control these systems. So solving is going to be much less of an emphasis. So, okay, if anyone has any questions about the overall setup for state space models, definitely feel free to ask now. All right, if we don't have any questions, the next topic I want to talk about is on linearity. So we say a state space model is linear if it can be represented in this form of AX plus BU. So A and B are matrices. And hopefully this form is quite familiar from our vector differential equations where we kind of continually wrote out like dx dt was equal to AX. So this was an example of a linear state space model, but as we're kind of going to see, not every state space model is in fact linear. Like, and a lot of the kind of behavior in the real world is nonlinear. So we're going to need to understand both linear and nonlinear systems at the same time. So just some examples we can quickly give. If we have a, I guess, continuous time system represented by this differential equation, we can write this almost by inspection in the form 2 minus 3, 4 minus 5 times x1 and x2 plus 1, 0, 0 minus 2 times u1 and u2. So you can say that this system is in fact linear. On the other hand, if we look at this second system over here, which is a discrete time system, you'll notice here that we're multiplying the two states here. And you can try as hard as you can, but you'll kind of realize that there is no possible way for us to actually write this as AX plus BU because these two states here have been multiplied together. So this is nonlinear, and it doesn't have anything to do with the fact that it's discrete. It's just because of the fact that we're multiplying these two states here together. Okay, so any questions so far about linearity, about state space? All right, moving on. Let's go to the discussion worksheet. So I've kind of given a brief summary of everything that's gone on in the first page. We introduced state space models, continuous and discrete time systems. So let's take a look at a couple of problems. And the main focus for today is really going to get you to think about how do I create a state space system? How do I pick state variables? How do I pick inputs? And how do these two kind of interact with each other? So it's kind of getting you to think about all these together. So in our first problem, we kind of have this trip planner who is setting up a bed and breakfast here, where at the beginning of each day, we're gonna do half the amount of dirty dishes in the sink. And then at each day, we're gonna have some guests who arrive and they're gonna add to the pile of dirty dishes. So we're gonna wanna set up a state space model to model this and also think about how this like behaves over time. So I'm gonna give everyone, let's say around 2 minutes to think about this. And then from there, we can kind of go over this together. So yeah, if you have any questions in the meantime though, definitely feel free to ask as well. All right, so hopefully people got the chance to take a look at this. So the first part asks you to define a state vector for the kitchen sink system and what are the inputs. So any ideas on what this can be? If you have any ideas, just feel free to type them out in the chat right now. Of our state vector. So remember that the state vector is something that changes over time. It's discrete and one variable, yeah. And what will that variable represent? We have a variable, or we have kind of the dishes the guests use. Yeah, that's a good thought. And I think really what's changing here though is the amount of dirty dishes. So I think the state vector I'm going to define is I'm going to define a vector x, which represents these are in units of pounds. So the the number of pounds of dirty dishes in the sink. Since this is really what's going to be changing over time. So as the guests use these dishes, we're going to add on to the number of dirty dishes. And then, do we have any inputs? If you think there are any inputs, type them out in the chat. Number of guests, yeah, I like that. So we're going to call the number of guests our input. And traditionally, we like to use the variable u to represent the number of inputs, which is kind of a convention in controls engineering. And then the last thing we need to do is to figure out what the state space model is. So I saw Eric earlier mention that it was discrete, and we can definitely use a discrete model. So at this point, it's basically a word problem where you can think about the dishes in the sink. Really, we want to define our state variable to be the number of dishes in the sink at the end of each day. So we can, or sorry, at the beginning of each day. So if you want to think about the number of dishes that are going to remain at the end of the day, that's going to be the same amount of dishes that are going to remain at the beginning of the next day. So you can think of that as x of t plus 1. And that's going to be equal to, well, Bob's going to do half the dirty dishes in the sink. So he's going to clear out half of what's currently in the sink. And then during the day, we're going to have guests that arrive. And the guests are going to use 4 pounds of dishes minus 1/8 of the pound, minus 1/8 times the number of pounds of dishes already in the sink. And the number of dishes already in the sink, you can think of that as like x of t. And because this is per every single guest, we're going to need to multiply all of this by u of t, which represents the number of guests. So this is going to be our state space model. So any questions about this? All right. And the next thing we need to think about is whether or not Bob's Kitchen is a linear system. And any ideas? If you have an idea, definitely type it out in the chat. Whether it's linear or nonlinear. No, because u is dependent on x, nonlinear. There is an x times u of t term, so no. All these answers are pretty good. U isn't necessarily dependent on x because like u is just a number of guests that arrive every day. Like u is a function of t. But it definitely is nonlinear because, as Alina mentioned, we have this x of t times u of t term here. So it's nonlinear because we have a x of t times u of t term. And after that, the next question, they're kind of going to talk about some planning problems. So I'll give you some time to think about this. It's getting you to kind of think about the problem recursively and work with difference equations. So. All right, hopefully people got a chance to start looking at this. So a lot of things going on, but I think once we put the math to it, it'll become easier, and challenge is always to turn words into math. So on Wednesday morning, there are 4 pounds of dishes in the sink. So you can kind of think of Wednesday as t equals 0. I like to think of it that way. It could be arbitrary, but just starting at a 0 reference is probably the easiest way to think about this. And because there are 4 pounds of dishes in the sink, like at the beginning of the day, x of 0 is going to be equal to 4. And then on Wednesday, we're going to have 4 guests. So this tells us that u of 0 is equal to 4. And then Thursday, well, Thursday is the next day, so we can think of that as t equals 1. We're going to have 5 guests, so u of 1 is going to be equal to 5. And then the question now is asking how many pounds of dishes are in the sink after Thursday. So after Thursday means at the end of the day on Thursday, or really the beginning of Friday, because Bob doesn't do any work overnight. And this is going to be t equals 2. So from here on, it's just kind of looking at our model and plugging in our values we have over here and working it out like step by step. So if we plug in t equals 0, we see that x of 1 is going to be equal to 1/2 times x of 0, which is 4, plus 4 minus 1/8 times x of 0, which is 4, times u of 0, which is again 4. So if we simplify this, this is going to be like 2 plus, let's see, this is going to be 1/2. So 4 minus 1/2 is 7 over 2 times 4. And if we simplify all of this, this is going to be 2 plus 14, which is then equal to 16. And then we want to find what x of 2 is, and it's just going to work the same way, where we plug in t equals 1. So just going to be 1/2 times x of 1, which we now know is 16. It's kind of very similar to recursion or dynamic programming, if you've ever seen it. And then we have 1/8 times x of t, which is 16, times u of 1, which is 5. So if we plug everything in, this is going to be 2. 4 minus 2 is 2 times 5, which is 10. So x of 2 is going to be 18, meaning at the end of Thursday, we're going to have 18 dishes in the sink, or 18 pounds of dishes in the sink, which is quite a lot if you think about it. All right. People get the chance to take a look at part D, or would you like some more time to take a look at this? Like a minute? Yeah, that's okay. I'll give everyone a minute for sure.
Is this asking us to have 12 pounds of dishes at the end of both of the days?
Yeah.
Or just at the end?
At the end of like just pretty much every day, really, or at the end of both days.
I see. Okay.
Okay. Hopefully you got a good start at this problem, but let's go over this together now. So as Bongi asked kind of earlier, we want 12 dishes in the sink at the end of each day. So we want x of 1 to be equal to x of 2 to be equal to 12. And we, as the trip planner, can control the number of guests that come to the restaurant. So we can kind of set up a system of equations and solve for the variables individually. So the u variables individually. So let's take a look at x of 1. And I guess before we look at x of 1, we can also note that you have 24 pounds of dishes in a sink initially. So x of 0 is equal to 24. And then from a recurrence, we see that x of 1 is equal to 1/2 x of 0 plus 4 minus 1/8 times x of 0, which is 24, times u of 0, which is unknown, but we want to solve for this. And this kind of tells us that, well, half of 24 is 12. 1/8 of 24 is 3. So then 12 plus u of 0 is, well, we want that to be equal to 12, right? So this tells us that u of 0 is equal to 0. And if you think about it intuitively, well, if you start with 24 pounds of dishes in your sink and you wash half the dishes at the beginning, and then you guests in, well, if you want to end up at 12, you got to just not let any guests in and just wash dishes all day. So it's kind of sad for Bob, but he's going to be washing dishes all day until there are 12 pounds of dishes. All right, moving on. If we look at the second time step, well, we can just do much of the same, where now we know x of 1 is equal to 12. And we can then multiply by x of 1, which is 12. And hopefully now u of 1 will be greater than 0. So we'll have some guess. But if we simplify all this out, 12 divided by 2 is 6. This is going to be 3 over 2. And if we subtract 4 from 3 over 2, that's going to be 5 over 2 times u of 1. And again, we want this to be equal to 12. So this tells us that 6 is equal to 5 over 2 u1, which means that u1 is equal to 12 over 5. And I think in this fictitious universe, we're going to assume we have a fractional number of people, even though it's not technically possible. If we were to actually model these, model the number of people as integers, though, you would kind of see that it's actually impossible to reach 12. You can get close to 12, but you can never actually reach 12. So, any questions about this part as a whole? This also just equals 2.4. But okay, if we don't have any questions, let's move on to the second question. And hopefully the first question gave you a lot of ideas and intuition how to model in discrete time, and the second question is going to go back to continuous time. So now we're going to take a look at this remote control hovercraft, which can kind of move in certain directions with a remote control. And we can provide some thrust to the hovercraft, but the hovercraft on its own also receives some sort of drag force. So this gives us some sort of dynamics in advance. So give everyone some time quickly to just think about the problem and read it through. And then we'll go over part A together, which talks about how to set up the states and how to define appropriate inputs for the system. Okay, let's take a look at part A now. I think really the question gives us the answer, but any ideas for what to pick for our state variables here? If we're interested in the position and velocity. And also, how many state variables do we need actually is the better question we should be asking here. So if you think about the hovercraft, and Eric luckily answered it here, it moves in both directions, X and Y. It's moving in like this 2D grid, so it can like move to the right, it can move up, and so on and so forth. And we're gonna need a total of 4 state variables representing the position and velocity in each direction. So hopefully this was a bit more intuitive. And we're gonna kind of treat velocity as a vector as well. So we're gonna look at like the velocity in both the X and Y directions. Okay, and inputs. Do we have any inputs? Well, we have a remote control, so hopefully that should give us a clue on what the inputs are. And notice how the remote control gives you a thrust in the X and Y directions. So I think picking WX and WY as our inputs will be a good kind of state variable to work it out. And if we were to put this in a vector format, let's define a state vector X, which contains X, Y, Vx, and Vy. So this is our full state vector. And then our input vector U is going to be Wx and Wy. So any questions overall on how to set up the state space equations? I think the last thing I also wanted to say was that you can always pick more states representing other quantities. You can like maybe pick acceleration as a state, but because it's just gonna add more variables for us to work with, we always want to try to pick like the minimal state representation that can represent all the information we actually need to solve the problem. So because here we only are interested in position and velocity, we don't need any more state variables. Do we need to include drag force? This is a really good question. So we don't need to include drag force yet because drag force represents the model here. So you might remember that when we were talking about state space, we have the states, the inputs, and then the equation here is the model. So because the question here is asking for just the, I guess, states and inputs, the model will come next. So we're gonna use this drag force to create our model, but we don't need to include our drag force as a state. Yeah, definitely a very good question. So the next part here, I'm gonna give use some time to work it out together in breakout rooms, is going to actually ask you to write out the model. And again, as I kind of hinted earlier, the model is going to be something of the form dx dt is equal to f of x and u. Given your states here and all the information up here on the drag force and I guess how these dynamics work together. And because we're not assuming any physics prerequisites here, we're gonna give you some hints. Newton's law tells us that like the net force on an object is equal to its mass times acceleration. So that's something to definitely think about. And then also remember that like acceleration is the derivative of velocity and velocity is the derivative of position. So let's take around 5 minutes to work on this in breakout rooms. And if you have any questions in the meantime, definitely feel free to ask before you join the breakout room about the question. All right. Looks like people are starting to come back. I think one of the challenges with these problems is always to set up the state space model. And normally, like, if it's any like difficult physics problem, we're going to give you all of the like physics dynamics to help you out. But I think this one is a little bit easier than the like other dynamics we'll give you. And just because it's like the first time we're looking at it, I think we want to get you to think about both the like how to set it up and how to like write everything out. So I think general advice I always like to give when anyone asks, how do I solve these, is to first take the derivative of all of your states. So if our state vector is this vector that contains our x, y, vx, and vy, well, let's take the derivative of everything. And that's going to be equal to, we kind of stated earlier that the derivative of position is velocity. And the derivative of velocity is equal to the acceleration. So now we kind of want to write out the acceleration in terms of the other states, or really the best we can. So next thing we should do is to follow the hint. Start writing out F net is equal to ma. And what are all the forces acting on the hovercraft? If you have any thoughts or ideas, type them out in the chat. I think looking at this diagram might help as well, but you might notice that you have a drag, yeah, and a thrust. These are exactly the forces we need to think about. And we don't have any other forces, so we just need to think about these two. So really, drag plus force, thrust, is going to be equal to ma. Because like F net just means the sum of all the forces. So I think I'm just going to think about these in both directions. So I'm going to think about it in the x direction. So the drag in the x direction, well, that's going to be from our input. That's just going to be wx. Sorry, that's not the drag, that's a thrust. The drag is going to be negative d times the velocity. That's kind of given in our problem over here. So that's going to be negative d times the velocity at x. So that's going to be our net force in the x direction. And that's going to be equal to the mass of the hovercraft times the acceleration in the x direction. And we can do the exact same thing in the y direction. This problem could get a bit tedious just because it's doing twice of the same thing at once. But from here, we can divide by m, and this gives us ax is equal to negative d over m vx plus 1 over m wx. And the same thing for y. And what do we do now? Well, we look back at our differential equation, and this kind of tells us that we've solved for ax and ay, and now we need to solve for vx and vy. So vx, you might recall, is the, well, vx is already a state variable, so we're good to go, right? So I think we can summarize this all up by saying that this is equal to vx, vy, and then negative d over m vx plus 1 over mwx, so on and so forth. And again, we're doing this all because, should be a y here, but we want to write the derivative of x as a function of x and u. And we kind of notice that all of these states here are really what the function is. So hopefully that clears things up. So any questions about how we got here?
Do you mind just explaining that step for the drag in the x direction? Why is it that times the velocity of x?
Yeah, so the force, you can think of the force as a vector, like fx and fy. And this is equal to the drag. The drag is a constant, right? Times like the velocity, which is a vector, and this velocity has like an x direction and a y direction. Does that help clear it up? I don't know if that was like.
Oh yeah. No, that helps. Thank you.
Okay, yeah, for sure. All right, so this is our state model now. And the next thing we want to ask is whether it's linear. So oftentimes these will be by inspection, but any ideas on whether or not it's linear? So can we put it into a matrix? I see a yes in the chat. I don't know if that was from my question, but it indeed is linear. And if you want to try writing it out, it is a bit like tedious, but like we can kind of look at AX as like X, Y, VX, VY, and kind of match it. Where this first row only has a VX. So everything is going to be 0 except for the third entry over here. And something good to think about is that your U vector is a vector in R2, and your state vector X is in R4. So if we want BU to also be in R4, then B needs to be 4 by 2. And A will always be 4 by 4, or really N by N, whatever the dimensions of your states are. And then doing much of the same. Our last line over here tells us that we have a d over m minus d over m coefficient, and then a 1 over m in the input matrix. So I think the last thing I kind of want to ask you as a kind of thought experiment is, why do we care so much about linearity? Like, why do we care if our systems are linear? Any ideas? I know, like,
Because we know how to solve them.
yeah, that's a good answer. So definitely something really good about linear systems is that this matrix A is a matrix, has eigenvalues. And as you were saying earlier, this kind of lets us solve it, but it also lets us like analyze it a lot easier because of these eigenvalues. And eigenvalues are going to be a big theme from here onward. Like, you can always kind of just break a matrix into just its diagonal form through diagonalization, and from there do a lot of analysis. So linear systems, as a result, become very predictable because you can look at them in the eigenbasis with just their eigenvalues. Whereas nonlinear systems, really, they behave however they want. Like, they just kind of go randomly. So I think actually the focus of tomorrow's lecture is going to be on analyzing nonlinear systems, so, and how to create a linear approximation out of those. Anyway, it is 12 o'clock, and I don't think there's anything too quite insightful out of this last part here, but I'll just give a brief explanation how to set this up and how this all works. So the idea here now is, given this big, ginormous system of equations, we want to solve for the position and velocity. So we want to solve for the vector x. And as we said, because linear is easier to solve, and the way we're going to do this is kind of take advantage of this like structure where we can just look at this bottom diagonal block. So we can write out this differential equation. Realize that the input is 0 because we don't touch the remote control. And then we just solve this, and then we realize that position is equal to the derivative of velocity. So to solve for the position, you just integrate the velocity from 0 to t. So that's about it. I don't think there's anything else too insightful. But any questions about how to solve this? Definitely encourage you to solve this in your own time. But okay, if we don't have any questions about this, that's the end of the discussion. So thank you all for coming. And if you have any other questions related to anything that we talked about today, definitely feel free to stay around and ask.